Today we want to look at transforming graphs. So if y equals f of x is the original graph, and this could be a quadratic, it could be a sine graph, it could be anything really. If we got the f of x plus a, that will move the graph up by a units. So if f of x was x squared, this would be x squared plus a. If it was sine x, it would be sine x plus a. F of x minus a will move the graph down by a units. So that'll move the quadratic down, and it'll move the sine graph down. And again, that will look like x squared minus 5, for instance, or sine x minus 3. The f of x plus a, well, what that's going to do is it's going to move it left by a. So whatever the graph is, it will translate it left, so parallel to the x-axis. So that'd be something like x plus 3 squared, or the sine of x plus pi over 2, for instance, and that will move it left by those values. The f of x minus a, then, it actually does it the other way, so it will translate it parallel to the x-axis in a positive direction, so to the right. So again, that would look like x minus 2 squared, or the sine of x minus 30 degrees, and that will move both those graphs to the right. The minus f of x, so that's the minus in front of it, what that does is it reflects it in the y-axis. So the quadratic would be reflected and it would look like a frowny face, and the sine graph would be the mirror image of it. Okay, and those would look like minus x squared or minus sine x. The f of minus x, that actually reflects things in the y-axis. So the y-axis is now the mirror line. So the quadratic graph, whenever you reflect it, it actually just looks the same. But the positive part of the quadratic would be reflected to become the negative part, and the negative part would be reflected across. The sine graph, it would be reflected, and it will have a difference. So this positive part will be reflected to the left, and then the negative part would be followed on. So it would be a complete mirror image of it, and it would be a different graph. And how that would appear would be the minus x squared, and as you can see, if you were to square out a negative x, you get a positive x squared, which is why the graph's the same. Or it could be the sine of minus x. So hopefully we can see the clear differences between the two. If we have the f of ax, where a is some scalar, what that'll do is it'll stretch it parallel to the x-axis. So we'll stretch it horizontally, it'll stretch it like an accordion, or move it in like an accordion, and it's by a scale factor of 1 over a. So if it was a scale factor of, if it was 3a, it would be brought in by 3 times towards the y-axis. If it was a quarter, it would stretch it 4 times away from the y-axis, and that would be the same for the sine x. And how that will appear would be 2x all squared, which would stretch it by a half, or it could be the sine of a third x, and that would stretch it horizontally 3 times. And af of x will stretch it parallel to the y-axis, so it'll have a vertical stretching going on, and it just applies it by the a. So again, what we would have is it could be 2x squared, it's going to stretch it vertically by a factor of 2, or it could be the 3 sine x, which will stretch it vertically 3 times away from the x-axis. So just a quick discussion about the sine graph. This is for a sine graph in degrees rather than in radians, but the same applies. It would just obviously be different in terms of the period. So the period is the length of time that it takes to repeat itself, and it will repeat itself every 360 degrees or every 2 pi radians. The graph has rotational symmetry about the origin with an order of 2, So hopefully what we can see now is whenever it's rotating, then whenever it's upside down, it looks exactly the same as the sine graph, and then it'll go back to normal again. So it's got this rotational symmetry of order of 2. We'll just wait until it comes back again. The other thing is that the sine of 180 minus x is equal to the sine of x. Sine is limited between -1 and 1, and sometimes we refer to that as the amplitude. So if you've done physics, hopefully you are familiar with the amplitude of the wave, and that would be 1 and -1 there. So the amplitude's 1. And y equals sine x is an odd function. If you think back to function notes, the sine of minus x is equal to the minus sine of x. So that's the definition of an odd function, is one where the f of minus x is equal to the minus f of x. And what that really means is if we were to apply this reflection, which is the one about the y-axis, it's the same as the reflection about the x-axis. So we have a similar story for cos x. We've got a period of 360 degrees or 2 pi radians. The graph has symmetry about the y-axis, so we can clearly see that's symmetrical. The cos of 180 minus x is the same as the minus cos of x. Also the amplitude, so it's an amplitude of 1, and the range is between -1 and 1. And this is an even function because the cos of minus x, so whenever we reflect it in the y-axis, it's going to equal the same function, and that's the function notation would be the f of x, or the f of minus x is equal to the f of x. And that applies to anything that is symmetrical about the y-axis. The tan graph is similar in a way, but also different, in that its period is 180 degrees or pi radians, so it will repeat itself every 180 degrees, and we can see that clearly because the asymptotes occur every 180 degrees. The graph has rotational symmetry about the origin of order 2, so we could turn it upside down and it would be exactly the same. The tan of 180 minus x is the same as the minus tan of x this time. Y equals tan x has asymptotes, so those are the vertical dashed lines. And the line, the graph, will get very, very close to, but will never actually reach. And that would be both in the positive and in the negative part of the graph. Y equals tan x has an undefinable maximum or minimum value. In other words, the maximum value is positive and the minimum, or the positive infinity and the minimum is minus infinity. And tan x is an odd function, and that means that if you reflect it in the x-axis, it's the same as reflecting it in the y-axis. So we get the same no matter which way we reflect it. I'll just quickly try and show that. So if we were to reflect this in the x-axis, this part of the graph would look like so, and we'd get a repeating form of that. So this is a reflection in the x-axis. If we were to reflect it in the y-axis, then this part is going to get mapped over here. This bit's going to get mapped over here. This is going to map there. This value will be mapped all the way back here. So what we have is actually just a repetition of the graph being reflected horizontally. And that's the definition of an odd function. So we had talked about this briefly at the start, about the sine x graph, but here we can see it a bit more clearly. So we've got the sine of x plus a, and it will translate it vertically by a units. So here we've got the sine of x plus 2, and all the values have been translated vertically parallel to the y-axis by 2 units. If it was minus a and it was sine x minus 2, then they've been translated down by 2 parallel to the y-axis. For a sine x, so if it's something like 2 sine x, what it does, it stretches it parallel to the y-axis by a factor of 2. So 0 has been stretched vertically by a factor of 2, so it stays on its own point. 90 has a value of 1, and it's been stretched up to 2. 45 would be a value of root 2, and it would be stretched up to 2 root 2. So root 2 has a value of about 0.7, and we can see this is around 1.4. 30 in here would be about a half, and then it's been stretched up to 1 because all the values have been doubled. The minus sine of x, so it's a reflection on the x-axis. So the 45 at root 2 has been reflected to minus root 2, 90 and 1 has been reflected to minus 1, 225 has been reflected down as well. So they've all been reflected in the x-axis. And for the sine of x plus a, which is the sine of x plus 90, that's going to translate it parallel to the x-axis to the left. So the red line is the sine graph. So if we go to 90 and 1, it's been translated 90 degrees to the left. 180 and 0 is then mapped onto 90, 0, and the same applies for all points. If we have the y equals sine of x minus a, so that's inside the bracket and it's a minus 90, so it's going to move it to the right by 90. So we've got 0, 0 has been mapped onto 90, 0, 30 and a half has been moved on to 120 and a half, and so on. So everything translates horizontal to the right or parallel to the x-axis. The sine of ax, so if we've got 2x, that's going to stretch it parallel to the x-axis by a factor of a half. Squeezing it towards or away from the y-axis is another way to think about that. So we're going to squeeze this in by a factor of 2. So 90 and 1 gets squeezed into 45 and 1. 30 and a half would be squeezed into 15 and a half. The period of the sine graph went to 360 and 0, and it's been stretched to 180. So the one full period of the sine graph has been then stretched into this blue one. And then that's going to be mapped in twice. We can see that. So if we've got sine of 2x, that occurs 2 full cycles within the one. And y equals sine x over a. So there are a couple of different ways that could be represented. It could be sine x over 2, or it could be the sine of a half x. And that way it's more similar to the sine of ax that we had previously. And what that does is it's going to stretch it parallel by a factor of 1 over a. So it's 1 over a half, which is 2. So it's going to stretch it horizontally by a factor of 2, and that's from the y-axis. So 0, 0 has been stretched horizontally to 0. 30 and a half is going to be stretched to 60. 45 and root 7 is going to be stretched to 90 and root 7. 90 and 1 is going to be stretched to 180 and 1. So it's stretched horizontally by a factor of 2. Now in terms of the sine graphs period, that was easy to say, we've got a full cycle within 360 degrees, but in the sine x over 2, we actually only have half of the period, so the period has been doubled. The amplitude stays the same, but the period has been doubled. And what we can see then is actually we only have half of a sine graph within the normal range. When we're looking at multiple transformations or composite transformations, we have to apply the stretches and the reflections before any translations. Brackets involve special considerations, but this isn't really on the course. So the way we think about it is kind of in terms of BODMAS still. So we do the multiplication before we would do the addition, and that would mean that we'd do the stretching before the movement, the translation. So think about BODMAS, and that's the way we do it. Now, if we were to consider this double transformation whenever it's inside the bracket, we do the reverse of BIDMAS. So for these ones, we do BIDMAS. But whenever it's inside the bracket, it always does kind of the opposite of what we think. So whenever it was 2x inside the bracket, it actually stretches it by a half. And if it was x plus 3 in the bracket, it moves it to the left by 3. So it's kind of counterintuitive, because plussing we normally mean to go to the right in a number line. So inside the bracket, we do the reverse order. So I suppose we would do SAMDIB inside the brackets. But then, as a whole, we would follow the BIDMAS. So if we have this example where this strange sort of trapezium-looking shape is our function, And what we're trying to do is do minus 2f 3x plus 1. Well, what we need to think about is BIDMAS. So we'll need to do the bracket first of all. Then we'll need to do the multiplication. Now we'll do that probably in 2 steps. So we'll multiply it by the 2 first of all, and then we'll apply the minus. So that'll be our 3rd step. And then the 4th step will be the addition and subtraction at the end. So we're doing the bracket, then we're multiplying by the 2, then by the minus, and then the plus 1. So the first step we can see has been done for us. We've stretched it by a scale factor of 1/3 parallel to the x-axis. That's because our rules of f of ax will be that it stretches it horizontally by a factor of 1/a. So the coordinates of 2, 5 has now become 2/3. 3, 5 has now become 1, 5. So it's all stretched in, and 6, 0 has become 2, 0. So everything has been stretched towards the y-axis. Then we've multiplied by the 2, so this is the a f of x, which stretches it vertically by a factor of a, and that's from the x-axis, so it's going to stretch it up and down by a factor of a. Now we don't have anything beneath the x-axis, but what we can see is that the coordinate 1, 5, or minus 2/3, 5, sorry, has been stretched up to 10. 1, 5 has been stretched up to 10. 2, 0 has been stayed the same because we're stretching it from the x-axis, and it's the same with the point minus 1, 0. So we're stretching all the y values by a factor of 2 in this one. So next then we've got this minus 2x, and with that we're reflecting it in the x-axis. Remember, we've got y equals minus f of x. If we've got our x-axis, it reflects it in that. So the point of minus 2/3 10 has been reflected to minus 2/3 minus 10, 1, 10 to 1 minus 10, and the points on the axis have remained on the x-axis. And then we've got this plus 1 to consider, and it's going to translate the graph parallel to the y-axis, so it's going to move it up by 1. So the f of x plus a moves it up by a. So the point of 2, 0 is now 2, 1. Minus 1, 10 is now minus 1, 9. Minus 2/3 minus 10 is now up to minus 9. And minus 1, 0 has been moved up to minus 1, 1. So the next example, if f of x is the cube root of x, express the following in terms of f of x and describe the overall transformation. So what we've got is, in example A, we've got an x minus 2, and we're doing that before our function. So if we think back to function machines, we've got an x value, we're putting it into some big function machine, and then it's coming out, and this is the cube root. But to get x minus 2, we're doing something first of all. So we're doing a take away 2, so that's going to be the f of x minus 2, because we're changing the x value to minus 2 first of all, and then applying the function, and that's going to translate horizontally to the right by 2 units. In example B, what we have is this time our function machine. We've got x is going into the box, and we're doing the cube root, which is f first of all, and then we're multiplying it by 3. So that's going to be 3 f of x. So we're working out the f of x first of all, and then we're multiplying it by 3. And what that does is it stretches it parallel to the y-axis by a scale factor of 3. So it's going to stretch it vertically by 3. Part C, we've got the cube root of minus x. So in our function machine, what we're doing is we've got x, and the first thing we're doing is we're doing minus x, and then we're doing the cube root. So we're applying the x first of all. So that's going to be the f of minus x. So we've got to do the bracket first of all before applying the function. And the effect that has is it's going to reflect f of x in the y-axis. Example example D, 1 plus 4 cube root of x. So let's think about that in terms of function boxes. So the first thing we've got is our x, then we're applying the cube root, then we'll be multiplying it by 4, and then adding on 1. So in terms of function x, so if it was the f of x, it's being applied first, and then it's being multiplied by 4. So that's the AF of x, and then plus b, or plus 1 is going to be a plus b at the end. And we'll follow BODMAS, just we've done there. So we're going to stretch it parallel to the y-axis by a scale factor of 3, and then translate parallel to the y-axis up by 1 unit. And then example E, what we've got is our x. The first thing we're doing is we're going to add 2 to it. And then we're doing the cube root. And then we're adding 3. So in terms of our function notation, we're going to do x plus 2. And then we're applying f. And then we're adding on 3. So the effect there is it's going to be translated parallel to the x-axis, 2 units to the left, and then translate parallel to the or the y-axis, 3 units up. So the 2 moves it to the left by 2, and the 3 will move it up by 3. This next example then, we've got the root of x graph being drawn for us, and then we've got the x plus 2 and then 2 times that. So in our function notation, we've got x, and then we're going to add on 2, and then we're going to do the square root, and then we're going to multiply it by 2. So that's function boxes. Function notation then, we're going to have the f of x plus 2, so we're going to plus 2 first of all. Then we're going to multiply it by a. So that's going to be a translation first of all, 2 units to the left, and then we're going to stretch it up by a factor of a. So we'll do this in two stages. We'll do the translation first of all, 2 units to the left. So 0, 0 is going to be moved to minus 2, 0. 1, 1 is going to be moved to minus 1, 1. 4, 2 is going to be moved to 2, 2. And what we should have is something that looks like that. Then we're going to stretch it vertically by a factor of a, which in this case is 2. So we'll do this in green, and it's going to stretch it parallel to the y-axis. So minus 2, 0 is going to remain where it's at. Minus 1, 1 is going to be stretched up to minus 1, 2. And 2, 2 is going to be stretched up to 2, 4. So that is going to look something like that. Question 3, by sketching the graph of y equals 1 over x, sketch y equals 1 over x minus 3 plus 4. So our function notation then, the first thing we're doing is we're taking away 3. Then we would be doing the reciprocal, which is the 1 over x minus 3, and then we're adding on 4. So the effect is it's going to move it to the right by 3, and then up by 4. So if we have the 1 over x graph, the reciprocal graph looks like this, where the x and the y-axes are asymptotes. So if we're going to move this graph right by 3, first of all, then the vertical asymptote is going to be moved right 3 units. So that's going to occur at 3. And the graph will look like that. Now we could work out the point where it crosses the x-axis. So this is really the graph of y equals 1 over x minus 3. So when x equals 0, we're going to have minus a third. Then we need to translate it vertically up by 4. So our vertical asymptote is going to remain unchanged at 3, but the horizontal asymptote is going to be moved up to 4. So the positive part of the graph is going to be moved up to the right, and the negative part we're going to have here, where this is being moved up by 4 units, so that's 3 and 2/3. And we could work out the x-intercept by letting the equation equal 0. So 1 over x minus 3 plus 4 equals 0. 1 over x minus 3 equals minus 4. So then x minus 3 is going to equal minus a quarter. So x equals 2 and 3/4. So that's the root of the graph. Question 4, write down the transformations that must be applied to the graph y equals x squared to give 2x squared plus 4x minus 1. And the hint here is to place it in complete the square form. So to do that, we'll have y equals, first thing we need to do is write it's 2 upon x squared plus 2x minus 1. And that's 2 upon, well, that's x plus 1 all squared. So we half the coefficient of the x, and we put it in here. But this is too big. This does not equal the x squared plus 2x, so we need to take away the square of plus 1. So whatever the term is that we've just put in as the second one in the bracket, we need to take away its square. And we've got this minus 1. So y equals 2 upon x plus 1 squared minus 2 minus 1. So y is 2 upon x plus 1 squared minus 3. So 1 squared is 1, minus 1 times 2 is minus 2, take away 1 is minus 3. So in function notation then, so if our f of x is equal to x squared, to get to our y, we have to add on 1 first of all to x, then we apply the function to get it to x squared, then we're multiplying it by 2 and then taking away 3. And that will move it to the left by 1. That's the first step in the bracket. Then we're going to stretch it vertically by a factor of 2, and then we're going to translate it down by 3. So writing that in a proper, coherent, mathematically sound sentence would be, we will translate it parallel to the x-axis by 1 unit to the left. Then we'll stretch parallel to the y-axis by a scale factor of 2, and then translate parallel to the y-axis 3 units down. Okay, here I've got the graphs drawn. So y equals x squared we know is the positive quadratic. Then we've got x plus 1 squared, which is translated it to the left by 1. Then we're applying 2 upon that, so it's going to stretch it vertically by a factor of 2. And we can see that it's the point, for instance, 0, 1 on the blue line has been stretched up to 0, 2. 1, 4 has been stretched up to 1, 8, and so on. Now it's getting a wee bit congested, so I'm going to get rid of the most recent one, or the previous one. Then we're going to do 2x upon 1 squared minus 3, which is going to translate the green one down by 3. So we've got a minimum point of minus 1, 0. It should be translated down to minus 1, minus 3. The point 0, 2 will be mapped down to minus 2, or 0, minus 1, if we've done it correctly. And we can see that that's true, so it's been stretched down by a factor of 2. Now, if we've done this correct, this purple line and the next one that we show should be exactly the same thing. And if I release it, it should trace itself on top of it, and it has. So these steps have been correct. So we've moved it to the left by 1, we've stretched it vertically by a factor of 2, and then we've moved it down by 3.